But for those listening, this is a written seminar for Multivariable and Complex Calculus. It's semester 1, 2017. You who are listening may be doing, say, Engineering Maths 2B. It will be useful for you as well. So the notation may be slightly different. So just be aware. I've been specifically asked to talk about doing the various integrals. Yeah, especially the ones that are involved in the various theorems. Because it's a classic exam thing, right? So verify whatever's theorem by doing both of these integrals. Because it both tests, I don't know whether it really tests whether you know how the theorem works, but it certainly tests whether you can do the integrals. So, alright. So, I don't know if the notation that I'm going to be using will match exactly with what's in your course. So I have printed out the lecture slides, but they're pretty basic in the sense. Okay, sure. Okay, so we're just going to have to deal with it. Okay, so the most productive thing I can do is to do an example and talk through some of the details there. And this is going to be Stokes Theorem. So, okay. Yep. And it goes like this question. Capital sigma is this set of points in R3. So x squared plus y squared is equal to z, and z is less than root of 4. Then w, which is a function of x and y and z. Sorry, I need to put the... Nope. There it is. Takes a lot to get an eraser out of that cup. This, which is a vector field, and we are going to verify Stokes theorem. Okay, I don't know what notation you use. Sometimes it's curl of W in this spot here. So it might be there. Your lecturer has the tendency to not put these dot product bits in here as well. And this is a capital S and this is a small s. Okay. Well, I guess the first thing is to try and figure out how to do any of these integrals. So I'm going to think about the this one first. So when I come to understand this, the curl of W is a vector field in its own right. So when you take a vector field, which has at every point a vector, you can open the little advent calendar window and there's a little vector there inside at every point. When you calculate the curl of that vector field, what you do is at every point you calculate a new vector, which represents some sort of swirliness of some kind. I don't really understand that part of it. But I do understand that it is some sort of derivative. And it's a derivative made out of, it's a derivative that is a vector. And so what we've done is we've taken our original vector field, we've differentiated it and replaced it with a new vector field, which is this curl of W. So the strategy for integrating that is really just going to be the same strategy as integrating any vector field, which is, well, we'll get to. But first we should figure out what that is. So the curl of W is the curl of this thing. Now, how do you guys go about calculating a curl? Do you do a little determinant thing?
Yeah.
So you do the determinant of
I, J, K, dx, second.
Ah, right, I get it. Sure. Gotcha.
A friend of mine showed me a trick that you can do, like, it's like you have like 1, 2, 3 at the top, that's the, so basically like it's, you have partial of F1, so you get partial of F3, partial of F2, partial of F1.
I'm just going to write down this version for the moment. I used to be really good at it and be able to do it without writing down the determinant, but that has faded over time. So I do know that it involves all of the derivatives that aren't in the divergence. So the divergence has each coordinate differentiated with the coordinate that it is, and all the other derivatives are in the curl. Because there's like 9 derivatives in your matrix, and 6 of them are in the curl and 3 of them are in the divergence. So that's one thing I do remember. So let's see. So you're saying I'm going to do this thing. Like that?
And it ends up being negative x, -1.
What? Don't tell me.
What?
I want to figure it out.
Okay.
I want to show figuring it out live. So, okay, so I'm going to get this one, and it's going to be that determinant there, which is that derivative of this, and that derivative of this. So d on dz of xz is x.
So isn't it going to be negative?
Yes. Because of that minus that. Sweet. And then we're going to have minus j, and that's going to be this determinant, which is going to be that there, which is 0, and d on dz of this, but it's going to be minus d on dz of that, so that'll be that. Sorry?
Yeah, it's positive, yeah.
But I put the minus, I put the extra minus in those, so that's okay.
No, it should be negative when all the minuses are done. Because you've got the minus from the term, and you've got the minus y, and then the minus from the j. That's 3 minuses, so you should have 1 by 3.
Oh yeah. Gooder, thank you. I really should have just done it with the i's and the j's and the k's in it so that I could make sense of it. So I times d on dy of 0 minus d on dz of xz, and minus j times d on dy of d on dx of 0 minus d on dz of minus yz, plus k times d on dx of xz minus d on dy of minus yz. That's the idea. Beautiful. I can do that. So this is I times minus x up here, and this is minus j times y, and this is k times z minus z. Is that right? So I've got minus x, minus y, and 2z, which is not on the screen. Okay, cool. Wow. Did you? Well, that's how I used to do it when I first started. I used to have this thing of knowing each position contains the derivatives of the other two. And it's this one minus that one, and then it's this one minus the next one, and then it's this one minus that one. So you just keep going from where you are. So let's just see if I can get that right if I do it that way. So I would get, this position would contain the derivatives of those two, and with respect to the other ones. So it'll be this on dz, and then this on dx. And the first one will be positive, and the next one will be negative. This position will contain the x derivative of that one and the z derivative of that one in that order, with the plus for this and the minus for this. And this position going around will contain the y derivative of that one and the x derivative of that one. So I mean, it's a memory thing. This doesn't mean that I don't have to remember much. I can just set it up and use something that I already know. But I didn't do cross products and that sort of stuff until I did second year. I'd never seen them before, so I had to get used to them in a different way. So, okay. Right. Cool, we've got an answer. And so this is the thing that I'm really integrating. I'm now integrating that. So what I really want to do is I want to do the integral of this. Dot ds. That's what I need now. I've replaced my curl with that thing. So the reason I need a dot product is that it's only possible to integrate a number. You can't integrate a vector. You have to turn it into a number in order to be able to integrate it, which is why we have a dot product here. Actually, when I'm on a surface, every little piece of the surface is going to be like a base for a little stack. So when I integrate with ordinary integrals, you know, each little piece of the line becomes the bottom of a rectangle. When I integrate on a surface, each little piece of the surface becomes the bottom of a little rectangular prism, and I just want to figure out how much of the vector field is pointing in the correct direction to be a height of that rectangular prism. And so that's why this ds here has a normal vector in it. So I do this, and then I imagine that this ds is a normal vector times a ds that isn't bulk. And that little ds here is a little tiny piece of area that belongs to the surface itself, that lives on the surface itself. Okay, so there's two ways of dealing with this. It may be that you have a really nice surface for which you know what the normal is at every point without having to do anything special. So if your surface is flat, for example, then the normal is always pointing straight up, and you can just go straight to calling that the straight up vector 0, 0, 1. But if your surface isn't flat, ours isn't, then that normal will be different at every point, and so we're going to have to do something special to figure out what it is. Right. And it turns out that that n hat ds is the same as, I'm going to need to parameterize my surface in order to do that. Okay, so I need a way of figuring out, no, I need to, when I do this, I have to track across the entire surface, and for every piece of the surface I have to multiply the size of this dot product by the area that's there and add them all up, and I have to track that across the whole surface. So the only way I'm going to be able to do that is to find a way of describing what every point on the surface is. I need to know where every point on the surface is so that I can track across the whole surface to do this integral. And so that means I'm going to have to parameterize the surface in order to do that. And parameterizing the surface will also give me a way of figuring out how big this little ds is. Okay, at the moment it's just this nondescript, very small sized area, which at the moment is not really described in any useful way. I presume that in every one of those little rectangles there's a little vector which describes the x-axis and a little vector which describes the y-axis inside that tiny little rectangle that's on the actual surface, little square I suppose. And those vectors would be 3D vectors, but what I really want is to describe the size of that relative to how quickly I'm moving across the surface as well. Because if I move across the surface more quickly than the x, y, and normal x, y, z coordinates allow me for, I'm going to have to adjust the size of that rectangle. So I'm going to have to do that too. So I'm just going to come back to this. I need to parameterize the surface. Which means I need to choose a way of describing what every point on that surface is. At the moment, my description of my surface is this, which does not tell me what every point on the surface is. This tells me if I have a random point, I can sub it into that equation and that inequality, and it will tell me whether that point is on the surface or not. But it doesn't tell me what the points on the surface are. We had this problem back in Maths 1A, actually back in Maths 1M as well, but we had this problem back in Maths 1A when we needed to find a basis for a subspace. Your subspace might be described in terms of an equation, and you wanted a description of what every point in that subspace was. And it would be t times something plus s times something. So we're going to do the same thing, only it's curved now. So we have to figure out a different way of doing it. So the best way is to imagine what that surface looks like. So it's a z equals, so I can imagine it as a function of x and y, meaning that there's an x and a y playing down the bottom, and then the z represents the height above that. So I know I can imagine it as a function of that, and it's z equals x squared plus y squared, and I know that that's sort of parabola shaped, because when I just pick the y to be 0, I'll get z equals x squared, that's a parabola in that direction, and I pick the x to be 0, that's a parabola in that direction, and in fact it's a parabola in every direction. This is an elliptic paraboloid in the language of Maths 1B. Okay? But I'm only allowed to use the z's that are less than or equal to 4. The other thing I can notice is that every possible z that will work is going to be positive, because x squared plus y squared is always positive. And so I'm going to get something like this. That's my x-axis and my y-axis, which I have just bent down to sit on the top of my table, and there's my z-axis there. And just to check that, if my thumb is the x-axis and my y is the z-axis, if my fingers are the y-axis, the z-axis should point out of my palm. That's the right-hand rule. Well, that's my version of the right-hand rule. It doesn't require me to do this, which hurts. Okay, and I know that it's like a parabola here and a parabola here, and it's sort of round, like that. And I can tell that as well because of this thing here. At every possible z, I get x squared plus y squared equals some number, and x squared plus y squared equals number is a circle. So it's a circle at every height. But I'm only allowed to go up to z equals 4. Okay, so what I would like is a thing that describes to me what every point on this surface is. So I could use the x coordinate and the y coordinate that every one of those things lines up with when I look at it from above. But the region of x's and y's that I'm going to use would be a circle then, which is fine, but it's going to be a bit tricky to decide what my limits for my x and my y are going to be that describe all of the points on this surface. It would be much easier if I could just say use all of these numbers from here to here and all of these numbers from here to here, and that's not how the x and the y is going to work, because there's a little shadow down here. They're the x's and y's that that's not picking up on the screen at all. They're the x's and y's that we're using, and I could choose x to be from -2 to +2, but then the y would go will be different range of y's for every x, and that makes it harder. And so I don't want to do it that way. So maybe what I could do is monopolize on those circles. Because what I could do is I could pick a height, and then given that particular height, I could pick a circle at that height. And I know how to describe a circle. It's got its own famous little parameterization for a circle that I can use. So what I can do to choose every point on that surface is I can choose a height, which would be z, and then I can choose a point on the circle x squared plus y squared equals z. That's my story of how I choose my point on this surface. Okay, so if I choose a point on a circle, that's going to be the x-coordinate's going to be radius cos theta, radius sine theta. That's what you'd get on a circle. That's how you make a circle. And then the height would be z. Now that doesn't look, I don't like those roots. That's going to make my derivatives a bit tricky. So what if I just called this r, and then that would be r squared. So I'm going to call that r. That should produce every point on my surface. So sigma is now r cos theta, r sine theta, r squared. For r between 0 and 2, I guess. The radius is 2 by the time I get up here. And theta between 0 and 2 pi. I suppose those should be closed and... Right, so I've now got a description of every point on that surface. That's my parameterization. I think your lecturer gives that a name as a function, I think. Normally something phi or something. Yeah? Like he composes it with the...
Yeah, fine.
Okay. Sweet. So now, my question is, as I move the r and the theta, that will produce all the points on that surface, which is good. I've been able to describe where all the points on the surface are. And so when I track my point across the entire surface, I'm actually going to track across the bays of r and the bays of theta like that. But now I need to figure out what happens to the little piece of area and how that's related to how fast I'm moving around that surface. Yeah?
So is that a general rule that essentially the number of integral signs you have is the number of variables that are going to be changing when you sort of get to the end of your integral?
Yes. Number of integral signs that are there is the number of parameters that are in your parameterization. And that's the reason they've been chosen that way, I believe. So when you do a triple integral over a volume, there'll be 3 parameters involved. Yeah. And so 3 variables to integrate over. That's a good noticing. It's important to notice things. Okay. I do have marks on the table here, but I keep losing them. I should probably colour in a bit more so that I know on the screen where I am up to. Okay. So, now what have I done now so far? I've figured out the thing that I'm supposed to integrate. That's this thing. I've figured out a description of my surface so that I can track some variables to move across the entire surface. I need to see how the little piece of area changes as I move across the surface. And that's my ds. There is no thing there. Okay, so the ds bold is a normal vector times a ds unbold, and this ds unbold is the size of the area, and this normal vector is normal to the area to point out what direction the area is facing. Okay, and it's got a hat on it because it's a unit vector. All right, and this turns out, luckily, to always be the derivative of this thing with respect to each of those. So we can talk about the size of that ds as how quickly a vector that's sort of tangent when I move the r and a vector that's tangent when I move the theta. So this all comes out to be the same as, and this is the bit where I'm just going to Yep.
I think this is where like
Your lecturer calls this like sigma or something in the lecture notes.
yeah, because I think this is where it becomes useful.
Yeah. So this function sigma, that's what he's going to call it. And so he's saying that it is the length of the cross product of sigma differentiated with respect to r and sigma differentiated with respect to theta times dr d theta. So this dr d theta is a little area. It's a little change in radius and a little change in angle, and together they make a little area when you join them together, when you multiply them by each other. Same as a little change in x and a little change in y would make a little rectangle on the xy plane. Okay, so I'm going to have to figure that out. So let's see. Sigma r, we've still got sigma on the screen. Alright, we differentiate that with respect to r, so we're going to get the cos theta counts as a constant, so we're going to get cos theta. The sine theta counts as a constant. That's my sigma sub r, the derivative of my parameterization using r. The derivative with respect to theta, r is a constant, it's multiplied on. The derivative of cos is sine. R is a constant multiplied on. The derivative of sine is cos. And that doesn't involve the theta, so that'll be a 0. And now I have to do the cross product of these two things. Okay. So in this position I'm going to have the determinant of that, sine theta times 0 minus 2r times r cos theta. In this position I'm going to have the determinant going the other way, so r times that, and that times 0. I just wrote that first column over here so that I could do it backwards. And this position I'm going to have that determinant, which is r cos theta squared plus r sine theta squared. Nice. Okay. So that was me shortcutting the cross product. Yes. Okay. So instead of doing minus this determinant, you can do the determinant of that with the columns the other way around. That's how a lot of people do it. Then they put the first coordinate here and do that determinant. Okay. And cos squared plus sine squared is 1, so we just get r in that spot. Alright, now I have to do the length of that. No, it's worth a try. Thought I could shortcut myself a little bit of work, but I'm just not going to do that. So I'll do the square of the length, so that'll be 4r to the 4 cos theta squared and 4r to the 4 sine theta squared and r squared, just squaring all three of them and adding them together. And so I get cos squared plus sine squared is 1, and that's what I get. I think I've done this right. So therefore the length of sigma r cos theta is whatever that is. I suppose there's an r squared in both of them that I could take out if I wanted.
Isn't it an R4?
I suppose there's an r squared in both of them that I could take out. And I but that now. Okay, good. Well done. See, I keep saying since the first years last week as well, wouldn't it be nice to take a team of people that could be watching your work and pick up on your mistakes in your exam? Yeah. Okay. So, there's a Barbie movie where all the princesses get a fairy to walk around with them. That'd be kind of useful too. Check fairy to check your minus sign errors. Okay, so what have we got now? We've got our ds is actually damn it. Done something wrong, just a second. Oh, for fuck's sake. No, don't do this bit. I don't want the length of it. I just want this vector. Sorry about that.
Well, if you want to find the unit normal.
I don't want to find the unit normal.
Okay.
All right. Yeah, sorry, I got myself a bit confused there. This is not true. This is true. Pretty sure. Yep. Sorry about that. Okay. Sweet. The reason this is true is that is a unit normal vector, sure, but we've multiplied it by a number which has made it longer. And this dr d theta doesn't really count as a size, and that is the size of this unit normal times that ds. It's been made a little bit longer. Okay, so I didn't need to do any of this if I didn't want to. That was not relevant for calculating my integral. So sorry about that. And I did such lovely work. You see, look at this thing where I figured out the square of it first without putting the root in first, because I didn't want to draw the root sign all the time. Anyway. If I was doing a surface integral of a scalar field, that I would have to figure that out. So that's okay. So with a scalar field, you have a d not bold s in this spot. And so you'll have to find the length of this. Yeah. Because a d straight s is the length of the d bold s. Yeah. Yeah, okay. All right. So what have I got now? I have figured out what my integral is now. So my curl became minus x minus y 2z, and my ds became this thing. Well, I'm just going to write this bit down. Sigma r cross sigma theta dr d theta. That's really small. I'm sorry. Ah, that's interesting. Just a second. This is all in terms of x and y still, so I'm going to have to sub in my r's and my thetas in order to do this. So let me just write some of those things down. So I've got my minus x minus y 2z is actually minus, now my x is r cos theta, my y is r sine theta, and my what have I got? 2z is it? And my 2z is 2r squared. Okay, I've subbed in, so sub in the parameterization. Okay, and then I'm going to need to dot that with my sigma r cross sigma theta. So my curl w dot ds I'll just do this bit. Sigma r cross sigma theta is minus r cos theta minus r sine theta 2r squared dot with my sigma r cross sigma theta, which is minus 2r squared cos theta minus 2r squared sine theta r. Right, going to have to dot them together. It helps to write them on top of each other because then everything lines up. So I get 2r cubed cos theta squared and 2r cubed sine theta squared and 2r cubed. Nice. And cos squared plus sine squared is 1, so I end up with 2r cubed plus another. So this bit here is that, and so I end up with 4r cubed. Nice. Beautiful. So what's my integral become? So it's become the curl of w dot sigma r sigma theta. I'm just going to put them all in so that you can see what's going on here. Like that. And we just figured out what this answer is. It's 4r cubed. Like that. And we're just going to have to tell the person reading it and ourselves what this sigma is in terms of the r and the theta. So the r is going... I can choose what order to put them in. Which one do you think it would be best to integrate first? Well, I guess the r is currently next to the thing and it's already in terms of r, so let's do that. So I'm going to go from r equals 0 up to r equals 2. That was the zone that I calculated earlier. Yep, r went from 0 to 2. And from theta equals 0 to theta equals 2 pi. Now I have carefully put in the names of the variables on my integral sign so I don't forget what they belong to. So you'll notice that going from the outside in, these are both thetas and these are both r's. And that just helps me keep track of what's being integrated when, and from both directions so I don't forget. Okay, so I'll do the outside integral. No, the inside integral, because you work from the inside out. Power up by 1, which would actually go up to 4. And we divide by the new power. Beautiful. So we get 2 to the power of 4 minus 2, 0 to the power of 4. Beautiful. And so that's the integral of 8. 16. Says the man with a power of 2 on his t-shirt. And so, when you integrate a plain number, you just get the variable attached to it. And so we get 16 times 2 pi minus 16 times 0, which is 32 pi. Yay! I expect there to be a pi there because it's round. Some things that are round don't have pi's, but usually it's because they're round in 2 different directions simultaneously. Okay. All right. So let's just see what happened there. What did I do? I had a look at the thing I had to calculate. I need to figure out a formula for what that was. In order to deal with the ds, I had to parameterize my surface, differentiate that in 2 different directions, and cross product them. And what that allowed me to do is have, so that's my curl, and that's my cross product. that I had to sub in the parameterization into the function itself, and then I could do the dot product, and then I could integrate it, because by now it's a number. You can't integrate it until it's a number. Okay. Well, that was what happened with that one. We've still got the other side to do. Now, fear not, because it takes me longer to do things while A, explaining it aloud, and B, figuring out what I'm doing as I go along. Hopefully when you get to your exam you won't be figuring out how it works as you go along. But if you do, at least you won't have to be explaining it aloud to other people, so you'll be faster. Okay, so I still have, now, to be honest, if this is the thing I wanted to calculate, and I've already done this one, I know they're equal, and so the other one must come out to 32 pi. But the purpose of this exam question is to show that you know how to do both surface integrals and path integrals, and so we're going to do the other one as well, because we're asked to. Okay, so let's figure out the other integral. So now we'll do that's a little s this time. Okay, so that's the boundary of my surface. That's the original vector field function. And this is a piece of a curve. The fact that there's a little circle in here is saying that this theorem only works if that curve is closed and comes back to where it starts. Okay, so in the other one, I had to figure out the thing that I was integrating. Well, I know what that is, just to remind myself. This is the original function. The original vector field. Okay? I want the boundary of this surface. So let's just redraw the surface so we can see where it was. So here's the thing. All of this part of the surface here is all enclosed. It's like a bowl. And it does have an edge though, this edge just here. Rather like this cup, right? Except, you know, my cup's flat on the bottom. There's the boundary of my cup, and all the rest of it's all filled in. And so that's the edge of my cup. And well, this is a cup too. So that's my boundary there. This bit just here. So that's a curve. This integral here at the moment, doesn't actually remember what surface that curve belongs to. Like once I've actually started doing this integral, I can forget that all of this other stuff down here is there. I can just focus on just this line. Curved line, but line all the same. So by the same reasoning in the other one, in the other integral I had to find a way of describing the location of every point on the object I was integrating over. I need to do that too here. I need to describe every point on this curve in order to do this integral. Yep?
So that would mean if we put our cup on front down, and the boundaries in the same place,
Yep.
we did the first integral, we get the same answer.
Yep.
What if it was like a cylinder, so you get the top bit and the bottom bit?
So a cylinder that was open at both ends, both curves are part of the boundary, and you'd need to integrate them separately and add them together. But they'd probably be going in opposite directions. I'm not quite sure on the details on that one. Yes?
And can I ask a really bad question?
No, you can ask a question and it won't be done.
Why isn't the actual curvy bit not considered part of the boundary?
Because wherever you are on this, you can move in both directions. Like you can move along the surface in every direction and still be part of the surface. No matter where you are on this thing, there are two directions to go to be part of the surface. But here, only half of the directions that you could possibly go from that point are actually still part of the surface. Yeah. I can, from here on the edge of my cup, I can go down here and be part of the surface, but there's this gap here if I go that way. So if I sort of maintain my being parallel to the surface, I've got all these directions I can go parallel to the surface, and I'm just still part of the surface or near it. If I go this way, I leave the surface completely, and so that's why it's part of the boundary. That's my first explanation that I just made up on the spot.
So you're
That
saying
makes
like,
sense.
you're looking at like a tangent plane, you sort of wrap that to your surface.
Yeah. And actually, tangent plane's a good idea. Like, the entire of calculus is about flattening things out. And so if you go in, zoom in far enough, it feels flat in that spot. So you have a tangent plane. So in essence, we're imagining that the surface could have been longer, and we just didn't go that far. So there's a tangent plane of the bigger surface sitting here, and some of it isn't above part of the surface, and so that's on the boundary. But when you're very close down here, if we zoom in on this bit with my little magnifying glass, there's a little piece of tangent plane there, which, no matter where I am on that piece of tangent plane, the surface is below me. Well, side to me, but if I'm standing on it as if I'm a bug that lives on this surface, I'm standing here, right? Right. Surface is below me. But if I'm here, what was that? Because he's not me. And there I am on this side. And if I go a little bit that way, there's nothing below me.
Well, it's like that scene from the next Divergence of X.
Sure.
No, like at the top of the nuclear power reactor and fighting dead people.
Sure. Why not? Yeah, God must be crazy. Throw stuff over onto the clouds, edge of the world. Eric the Viking. Good movie. You've never seen Eric the Viking? It's fabulous. Fabulous film. Completely ridiculous, as most fabulous films are. Okay, so we've found the boundary. We need to describe every point on that boundary, the same as we described every point on the surface in order to integrate on the surface. So we need to parameterize the boundary. Okay, so let's have a look at this. Every point on that boundary is at height 4. So I know that the z-coordinate on the boundary is 4. Because they're all at height 4. And and it's a circle of radius 2, because remember it was z equals x squared plus y squared. So if we're here at an x coordinate, where the y coordinate is 0, the x coordinate x squared would have to be 4. So that's 2. So it's a circle of radius 2 at height 4. And so we get 2 cos theta, 2 sine theta. Okay. That's my curve. Now, I used exactly the same thinking that I used to create my surface in the first place, which is one of the reasons why it was so useful to use the other parameterization. So the old parameterization imagined my surface as being made out of a whole lot of little circles that were stacked on top of each other. And so it's very useful to do, I just basically did my old parameterization but picked r equals 2, and it gave me my boundary. Yep.
I learned past that sometimes you can get called up for orientating this the wrong way.
Oh, okay.
Oh,
So, yes?
the negative flippy thing.
I think that's a different orientation thing.
Isn't orientation supposed to be if you're walking around it's like inside of the thing or like
The
Isn't it the direction that you're going? Like,
Because I remember there is a the cross product in between your normal, your velocity and I think the space or something.
There is a thing. But to be fair, if we've done it wrong, our answer will just come out to be minus what it should be, and we can go back and change all our minuses.
But if it's not a verified, what is it just calculated?
True. Well, let's just have a look at where our normal was pointing in the other one, right?
Given the question, it did say somewhere along the lines consider that the normal should have a positive z.
Okay. Well, let's just figure that out just a second. So our normal is pointing in this direction. That's not the unit normal, but it's the correct direction. And the r is a positive number, so the z-coordinate is positive of this normal vector. That's great. And that means it's pointing generally upwards. So if I'm sitting on my surface, that's downwards from my perspective standing on the surface, because the normal vector is pointing that way, right? Upwards. Upwards in space, which is inwards for this surface. Traditionally, you do them outwards, but that's okay. So, I think you need to follow the right-hand rule based on the direction that things are pointing as they point through your curve. So, my normal vectors down here are all pointing towards this. They're all pointing that way. And so if I point my thumb in the direction that the normal vectors are pointing as they pass through here, my fingers on my right-hand rule curl in the direction of the positive direction on my curve. I think that's correct.
Oh, that's right, yeah, because you've got to have the thumb is your normal, then you've got the direction that you're travelling in, and then the third one has to be in the surface.
Well, there's two right-hand rules. Yeah, there's two right-hand rules. There's the one where you've got...
Sorry, how did you draw the arrow again? Sorry.
I went... All my normal vectors are pointing upwards through here. And so I point my thumb in the direction of the normal vectors, and then the direction that my fingers are curling is the direction that my arrow goes around my curve.
Oh, that's cool.
I think.
Do different directions make it easier or harder to...
Don't think it makes any
No, it's
difference.
just the same thing,
You just come out of minus.
Yeah.
If you go the other way, it'll just be minus. Same as with ordinary calculus way back in Maths 1A. If you did your integral backwards from like 4 back to 2, you get a minus answer.
Yeah.
So, okay. Glad that we brought that up because I wouldn't have mentioned it.
And just to clarify, so if we did, back when you did the cross product, if you did it the other way around, so sigma theta cross,
Sigma r.
then we would need to do the boundary going the opposite way to get the same answer?
Yes. Yeah. Now in this question, the lecturer, in this exam, the lecturer specifically said they wanted this third coordinate to be positive. So if you had done your cross product the other way around, you would have just said, but we needed that to be positive, so we'll do the other cross product. So if when you did this come out to be minus r when it's sigma theta, sigma r, you would have said, well, we need a positive third coordinate, and so we'll instead calculate sigma r, sigma theta.
Or you could just say u cross v is equal to negative with v cross u.
Exactly.
And then put minuses where you had positives.
Yeah. Yes, that's exactly how I meant to do that. You would calculate this, and if it came out as negative, you'd just go, well, the sigma other way, the cross product the other way around would be, and you would write this down with all the minuses the other way around.
And if it didn't specify,
You get to choose.
but you did say normally you want to have it pointing outwards.
Yeah, traditionally it points outwards from your surface.
So
If,
we should have picked the other one.
Yeah.
Choice.
yeah. So traditionally, if you have a concept of what the inside of your surface is and what the outside of your surface is, it normally points out. However, I think the reason the reason that he has chosen to do it this way is so that this is going anti-clockwise, looking from above, which is your traditional direction for a curve. Because if we had gone the other way, we would have had to go this way, and that would have been harder. We would have been going from 2 pi back to 0, because we're going the opposite direction.
Which
Yeah.
means classic exam, if he's going to flip our shape upside down, we'd have to be more careful of which way it's going to go. Because
Yeah. All right.
Just out of curiosity,
Yep.
how would you describe that shape upside down?
What would go up here?
Yeah. So if you had the northern hemisphere against the X, like that, how would you describe that?
Well,
If it tracked from 0 to 4, how would you describe that?
this is 0 here.
Yeah, and then it goes up to 4.
Okay. Well, it's probably one of these. Not quite in the right spot yet, but I'm nearly there. So this one here is z equals x squared plus y squared. So z is minus x squared plus y squared would be down there. It would flip upside down, right? And I have to shift the entire thing up 4. Because that adds 4 to the z coordinate is whatever the z coordinate of this is plus 4. So that's where I would put it.
That shape have a name?
Well, they're both just elliptic paraboloids. Elliptic paraboloids. Paraboloids because if you slice them in 2 different directions you get parabolas, and elliptic because when you slice them in the other direction they're ellipses. Circles are just ellipses. Special ellipses. But ellipses nonetheless. Okay, cool. We're doing really well, I think. And I'm not losing the order of my pages, so we're doing even better. Okay, so we have now... Okay, so at the moment we've figured out what our function is. We've figured out what the object that we're integrating on is, and we've got a parameterization for it. Doing really well. And now we just need to deal with our ds. Okay, so it's a little s because it's a piece of displacement, s for displacement back from physics. It's a little piece of displacement, a section of the curve. So what we imagine is that here we are on the curve and there's this little tiny piece of curve just there. And it's a bold s because it has a direction. And the really nice thing about that is that is the speed, that's sort of like the tangent to this curve, and it's how quickly this curve moves along when I move along my theta. So as my theta moves, this will be different sizes. Well, in this case it'll always be the same size, but for some curves it's different sizes as you move along. So this ds is going to be, a derivative. It's going to be the derivative of this thing. Now they normally call that gamma, don't they? Gamma, because in Greek it makes a gut sort of sound, and kut for curve. It's the third letter of the Greek alphabet gamma, and our third letter is C, kut, so it's kut for curve. And the reason it's called sigma back there is the sigma is the S sound for surface. Sometimes multiple things. Okay, so this is going to be the derivative of gamma, which is a vector, times ds, where s, or actually d theta. Right. Pretty sure that's right. Let's just check. Sorry? Just want to be absolutely certain. Yep, that works. What? Alright, cool. I think I'm good. Right. So, I mean, this one makes the most sense in my head is because the idea is that when the theta moves a little bit, it causes the s to move a little bit, and the direction that the s goes is this derivative. That's what derivatives are for. And so this is, the derivative of cos is minus sine, not minus cos. The derivative of sine is cos, and the derivative of 4 is 0. Beautiful. Okay, so my integral now becomes this. My w is whatever it was. Okay, just going to leave it at that for a second, and we'll just sub in all the things in a minute. This is going to be easier to do if I figure out what this is first before I do anything else. So I really should have written that right at the beginning. That would have made my life so much easier. But I didn't define what gamma was until later. So okay, so w dot gamma dashed is y z x z 0 dot sine theta 2 cos theta theta. Oh crap! This has got x's and y's, and it's supposed to be in terms of theta, so I'll just have to sub in my thetas. That's what they mean. He means by doing the function composed with the gamma. So let's see. The y is 2 sine theta, and the z is 4, and the x is 2 cos theta, and the z is 4. I really should have gone back and just written what w was in this thing without doing the dot product, but anyway, I'm committed now. Okay, so what have we got? Minus 8 sine theta, 8 cos theta, 0 dot with minus 2 sine theta, cos theta 0. So we get 16, yep, sine theta squared and 16 cos theta squared and 0, which is 16. This is looking like it's going to turn out nice. And then we have the integral that we really want. So it's going to come out to 16 d theta, and my integral is now tracks across all the values of theta that define my thing. So it's from theta equals 0 to theta equals 2 pi, which is going to give me 16 theta from 0 to 2 pi, which is 16 times 2 pi, which is 32 pi. Yay! And it works. Yay. Right. So, what did we do there to do a path integral? We had to figure out what function we were going to do the path integral of. We had to parameterize our path, but because we were doing Stokes Theorem, we had to be careful about which direction we parameterized it in, sadly. And that was based on a right-hand rule that's, so if I go back to the normal vector in the other bit, I can make sure I stick it in the right direction, which is interesting because you'd have to make a decision about the other one. You'd have to make a decision about what direction your normal was in. But that'd be like in physics where you choose a direction to be positive, like maybe this way or this way. So as long as you choose which direction is positive, you can do your right-hand rule based on that. Okay, beautiful. And then we had to differentiate our parameterization in order to figure out what ds is, and then we can do the dot product, and then we can integrate it. Because by the time the dot product has been done, it's become a number, and we can integrate a number. Okay, beautiful. Where are we up to?
Is it like possible to put all of these steps in like general big box things, like this is everything you've got to do?
You want me to do that now? Is that what you asked me to? Did you want me to do that, or?
That would be good.
What time is it? Oh, good. Because that clock says it's 3:15, and and that would mean I'd be going, and I haven't talked about volume integrals yet. Okay. So just a second.
Well, if you really want to include
Okay. Though I should say that that's a good thing to notice, that you have noticed very cleverly that I have been every couple of minutes, every time I had finished a piece of it, to go back and figure out where I was up to. That's a good strategy, both for exams and for teaching. So that, and not just for you, but for me, so I know where I'm up to, so I don't lose track. Okay, so do we have some other examples of things like this that you would like me to, that that actually have functions and stuff in them that you want me to do? I suppose it's like Gauss's divergence theorem is one of the others, isn't it? All right. I'm just going to go back to the beginning and say this one was a Stokes theorem thing. All right. So I just need an example of that. Has anyone got one?
I did have this.
I did have this like on my laptop, but I didn't bring it, so. That's okay. Oh, so you mean this next question?
Yeah.
It doesn't have Gauss's divergence theorem in it. It is just a triple integral, but I may come back to that. Can I do a Gauss's divergence one, or do you want me to just do a triple integral?
In 2016, there was one where you could use Gauss's divergence, or you could just
Do it.
2016 should be number 5. If there's a calculated volume is a just change in variables triple integral in the
I will write down the relevant bits of this. This one here, number 5. Ooh, what year was this? Last year?
last year's.
Do you know if? Did you have Thomas this year?
Yes.
Did Thomas do it last year?
Yes.
Look at him labelling them to tell you what the question's about. That's so nice. Wow, okay. Anyway, so W is this thing. He's called that a transformation, but I have a feeling that's really just going to be a parameterization of that thing. Okay, sure. Compute the volume, compute the flux integral for that vector field. Hence, you may assume that W satisfies the assumptions of Gauss's divergence theorem, or you may compute the flux integral directly. So that flux integral is a surface integral. Okay, cool. Well, we'll do the volume one first, and I'll see if I have time, and I'll do the surface one again. Okay, so what we have is we have this region. I'm going to ignore the r cubed if you don't mind. That's a Z. Okay. I'll do all the other stuff in a minute. Oh, interesting. All right. And we have a function. Yep. And I'm going to just pretend that this is what the question was. Now, how does this go? The divergence on the volume is the integral of the divergence on the volume is the integral of the original function on the surface.
Yeah, but the divergence has to be composed with the parameterization in order for you to be able
Yeah. I'm all good with that.
to do things with it. Otherwise, that's explode.
That is divergence theorem.
Yeah.
Okay.
That's a capital, that's right, because you can surface.
Yep. Okay, so let's just check I've got everything right here. Yes, this is a surface. It's a double integral, so that'll be a capital S. We have to have a dot product here. Even if we don't write it, we know it really is one, because you can only integrate a number. dv, the divergence is a number, and so this dv will be a number as well, not a vector, because you can only integrate a number, not a vector. Number times vector would have been a vector. Okay, beautiful. And I also know that I've got this round the right way because the divergence is a derivative, and when you integrate a derivative they should cancel each other out, so you should end up with a double integral. If you do a triple integral of a derivative, one of these integral signs will cancel out with the derivative. That's how all of these ones work. They're all, some people call these the fundamental theorems of calculus. The ordinary fundamental theorem of calculus says that when you integrate something that's already the derivative of something, what you get is just the original function. Integral and derivative cancel each other out. Green's theorem is the double integral of a derivative thing is a single integral of the original function. Yeah, I know. And I didn't even learn that until like after 2 years of helping people with multivariable calculus, and I'm pretty sure I did some multivariable calculus as part of my degree, and I didn't know it then either. Okay, so that helps me remember what goes here.
So the divergence is saying because the divergence is like a derivative,
Yeah.
it kills one of the integrals, which is why it turns it from the triple integral to double integral.
Yeah.
Whereas in Stokes, you start with a double integral, but you've got a curl, and that curl
That's a
is
derivative, and it
which kills one of your integrals, which is why it turns it
to a
into
single integral. Yeah.
That's cool.
In Green's theorem, it's a little less obvious, but you do have derivatives. Like it's dp on dq, dp on d something minus dq on d something. So you have a derivative over there with a double integral, and then it becomes a single integral on the other side. Yay! Okay. So, I'm going to do this volume one first, because I can do that. Yeah?
But that would also then explain why we might have the whole surface and then the boundary would usually be one less dimension.
Exactly. Yeah. Just like with ordinary integrals, you have a full line, and when you calculate it, you just use the two endpoints. So the endpoints are the boundary of the line.
Yeah.
And the curve is the boundary of the surface. And the surface is the boundary of the volume. Everything's coming together. Okay, so we'll do this one first. I'm enjoying the tuneless whistling. Okay, so I'm going to need to figure out what function I'm integrating, which is this thing here. So I'll just need to calculate the divergence of f. So the divergence, if I'm very clever, I can fit them all on the screen at the same time. The divergence is the integral of each position with the variable that would normally describe that position. And so the derivative of the what's in the x coordinate with x and then what's in the y coordinate with y and what's in the z coordinate with z. This time it's not the best example because we've got an x in the x position and a y in the y position, so we've got to just beware of the toast. It doesn't always work that way. And we could have any function there. It could be x squared, and in this case this would be a 2x. It could be a yx in that first position, in which case it would be a y when I differentiate it, so just be careful. To be fair, I could probably put any function I wanted there. Maybe I should pick a different one, but anyway, I'm just going to run with this and see what we get. Okay, and so I get 1 plus 1. Oh, do you know what? I'm going to change the function. To x, y squared. Just because. Hopefully it's not going to get too much worse. Yeah, suddenly it takes 5 hours. Okay. So the derivative of x, y is y, because the y counts as a constant in that one. The derivative of y squared is 2y. See, that's not going to be too much worse. All right. Okay. And now traditionally dv is x dx dy dz. I mean, that's what that is. It's a little tiny piece of volume which is made by tracking across the inside of that volume, and if I move in various different directions simultaneously, it'll make a little box. So if I move my x, y, and z maybe a little bit this way, there'll be a little box that sits inside, and that's the dx, dy, dz. We multiply them together to get a volume. The problem is that my surface may not be very easy to describe in terms of x and y and z. So let's just see how that turns out. Because again, I'm going to need to describe every point on my surface somehow. Not surface, every point in my volume. Okay, just the same as with my surface integral, I had to describe every point on the surface, and with my path integral, I had to describe every point on the path. With my volume integral, I have to describe every point in my volume. Okay, so at the moment, I should really just imagine what that volume actually is. So let's see, just so that we know, w is x squared plus y squared. Okay. Now I know that if x squared plus y squared was equal to z squared, that would be a cone. That's from Maths 1b. But I do know at least that at every z, when it's equal to z, it's a circle, right? X squared plus y squared equals z squared is a circle of radius z. So for fixed z, x squared plus y squared equals z squared is a circle of radius z. Beautiful. And since it's less than or equal to, I want the inside of the circle. Okay. And when z is 0, I get a point, because it's x squared plus y squared equals 0. And if I looked at it when x is 0, I get y squared equals z squared, which is the same as y equals plus or minus z, so it has straight lines on it when you cross it vertically. So it's going to come out like this. That's really faint. But I only want the z coordinates to be between 1 and 2, okay? Sure. Where'd my nice coloured ones go? There we go. So that's z equals 1 here, and that's z equals 2 there. All right, a frustrated cone, which is my favourite 3D shape. Well, other than a silver rhombic dodecahedron, but it's my favourite 3D shape with curved faces. So, okay. Okay. Right. Sure. All right. So let's just think about locating every point within that using the x and the y and the z coordinates. I could choose the z coordinate, that wouldn't be too hard. And then I could choose within that the x and the y coordinates, but again the x and the y are within a circle. So if I was at a specific height, maybe at the top here, I could choose my x to be between 2 and minus 2, but then my y would be different for every x. And that would be okay, but it's harder to describe where everything is inside that volume. And so having something that's based on parameterizing the circles, and I can imagine this as being made of sort of a circle at every height made up of little circles inside it, that can be my way of parameterizing this surface, not surface, volume. So I can say something like choose my z, and then I can within that we can choose a radius up to z, which I shall call r, and then there'll be a little circle at that height within that bigger circle, which will be r at height z of radius r. So I'm going to have something like r cos theta, r sine theta, z. Is that how they parameterized it? No. Oh, clever. Okay. Yes. Well, this is going to be a problem, right? Okay, this is nice. This is nice. Except my r will be different at every z. I'll have a different range of r's to choose from at every z. If my z is 1, I'll get my r will go from 0 to 1. If my z is 1.5, my r will go from 0 to 1.5. I'd really prefer the r to not be dependent on one of the other variables. And so what I can do is I could say, well, what if instead of choosing a radius up to z, I could choose a percentage of z that radius corresponds to. So what percentage of the radius am I going to go to? I can have, 50% of the radius, 75% of the radius, and I can choose my r. I can choose, okay, so choose radius up to z. We're going to say the percentage of the radius up to z. That's what my r is. It's not really a percent. I suppose it would be a proportion. Okay, so the big circle was z cos theta, z sine theta, the one on the outside of this height, and ours is that percentage of it. Beautiful, which corresponds perfectly to This. He's just used v instead of z, but whatever. And actually, it is tradition to even if you're using one of your original variables as one of your new variables, it's tradition to change the label so that you don't get confused along the way. So we're just going to change the label to be something else. Okay, so we're going to say, your lecturer has used v, so why not? Such that, let's see, the r is between 0 and 1 because it's a percentage. The theta would be between 0 and 2 pi. And the v would be the value of z when that's between 1 and 2. Now you don't have to do it that way. I could have specified that the r is based on the z, and that would have been okay, and I would have been able to do my integral if I did it that way. But this is just going to make my integral easier, because all my variables are independent of each other's choice. Beautiful. Okay. So what that means is I'm going to have to switch all my variables, right? My original function was written in terms of x and y. It's 3y here. And my dv was dx, dy, dz. So I'm going to have to transfer everything to be in terms of r, v, and theta, in whatever order I think is best. All right, here we go. Okay, so let's see. My x coordinate was rz cos theta. My y coordinate was rz sine theta. And my z coordinate, v was v. So to change my variables, my vector dx, dy, dz is going to be another vector of matrix times the vector dr, dv, d theta. And then I'll do the determinant of that matrix to figure out what the multiplication dx times dy times dz is in terms of dr times dv times d theta. That's how you do it, isn't it? You do like your Jacobian matrix and you... Sweet. Now, I have real trouble doing it. I have real trouble doing this without writing the matrix, so this is my thought about this. And I'm going to do it rv theta because that's the order they're currently written in, and it'll just be easier to inside this variable. So, beautiful. I'm just going to put my dx, dy, d theta up, dz up here just to remind me what's going on. All right. So dx will be, the change in x will be related to changes in r and changes in v and changes in theta. And so I will have dx is going to be curly, the partial dx on dr times dr, the partial dx on dv times dv, and the partial dx on d theta times d theta. So these ones are going to go here. Yeah. Okay, so let's see. dx, but I have to write this or I can't remember how to do it, so just for me. Okay, so x was this, dx on dr would be v cos theta. I need more space. So, dx on dr is v cos theta, dx on dv is r cos theta, dx on theta. That's totally wrong. I'm just going to run with it. It's actually this way. dr dv. Okay, dx on d theta is minus rv sine theta. dy on dr is v sine theta. dy on dv is r sine theta. dy on d theta is rv cos theta. Oh, damn it. dz on dr is 0, dz on dv is 1, and dz on d theta is 0. That's an r and a v. That's a v. How's that? See, I knew I should have used u. V's and my r's are too similar. Okay. So at this point, I know what I'm going to need to do is the determinant of this matrix. So I know that dx, dy, dz is going to be the determinant of this matrix times dr, dv, d theta. I'll probably need more space to do that determinant. However, I do have a row with lots of zeros in it, so I will expand the determinant along that row. So let's see, we have plus, minus, plus. Okay. So plus 0 times stuff, minus 1 times v cos theta times rv cos theta, which is rv squared cos theta squared, minus, looks like it's rv squared sine theta squared. Oh, and look, sine squared plus cos squared. Okay. I need to be the absolute value of this. Because it's a relationship between volumes. Volumes can't be negative. Yeah, that's why. And so that minus will disappear, and I'll get rv squared. Which is nice because v squared r. Good. That's what I was supposed to get according to the thing. All right. So what I've been managed to do is we managed to be able to replace the dx, dy, dz with something else. So let's just see where we were up to. We've divergence of f dv. Okay. So the divergence of f was 3y, and the dv was dx, dy, dz. But now the y is now rv sine theta. The dx, dy, dz is now rv squared dr, dv, d theta. And my r goes between 0 and 1. That's the wrong direction. The r is here, so this r is here. It goes between 0 and 1. The v goes between 1 and 2. And the theta goes between 0 and 2 pi. Okay. Beautiful. I could choose which order to do them in. And the reason, one of the reasons to choose your variables so that they're independent is that it's easier to switch the order of your integration because they're independent of each other. So, just a second. Interesting. Well, I suppose it doesn't really matter what order I do them in. I should simplify it first though. All right, let's do it. So my R. That's what's going to happen. This and this and this are all constants, so they'll still be there. And the, oh wow, this is really, sorry? Yeah. The R will go up to 3 and I'll divide by 3 and they cancel. Very nice. Sorry? What? And so I'm going to have to sub in 1 and 0. If I'm strapped for time, I will just note that when I do sub in 0, the answer is 0, but that doesn't always happen, so I'm going to do it explicitly. And that does work. But just be very careful, some functions when you sub in 0, they're not 0, and so you don't get one part of it disappearing. Okay, so I'll integrate that v to the 4. Actually, it's not rigged. I changed the function.
Lucky yes.
So let's see, that 1 is not really there. The v will go up to v to the 4. But nicely, 2 to the 4 will cancel out the 4, this is nice. Now I can write exam questions. Yeah, I know. Now that's a fun exam. Come in, person stands there and makes up an exam question for you on the spot.
They get the same amount of time as you get.
Yeah.
To write and run solutions.
Okay, so that disappears. 2 to the 4 is 16, so I've got... Thank you. Aha, look at that, it doesn't disappear. Oh, see, not so pretty. Damn it. Okay, so 2 to the 4 is 16. And then divided by 4 would be 4. And so that's 4 sine theta. Minus a quarter of sine theta would be 3 3/4, which is 17 quarter, 15 quarter. Yeah. I wish mathematicians weren't so down on mixed numbers, because I would totally just write 3 3/4. But, you know. And that I can do. That number's still there. Only the integral of sine is minus cos. Sometimes it does come out to 0. And so we have minus 15 on 4 cos of 2 pi minus 15 on 4 cos of 0. And cos of 0 and cos of 2 pi, it is coming out to 0 anyway, isn't it? Yeah? Yep, cos of 2 pi and cos of 0 are both 1, so we get 0. Aww. Oh well, there you go. No, it doesn't have 0 volume. The divergence of that function added up across that volume has 0. That's an important thing to point out. I am not calculating a volume here. I am calculating, if I want to be philosophical about it, I'm calculating the hypervolume of a 4-dimensional thing. If you really want to do it. I'm doing the average value of the divergence across this multiplied by the volume. So on average, the divergence across here is 0. So integrals are really averages, in a way. Right. so where are we up to? That's not telling me the real time. Okay, I've got enough time to do the surface integral that goes with this too. Right. But let's just see where we were. So I had to figure out the function that I was integrating, which I did. I had to remember what dv stood for in terms of other d's. I needed to, just like with everything else, find a description of every point in W. Oh, no, that's not that page. That page. And that means a parameterization. Now, if in the exam they told us what the parameterization was, so we can run with that. But I just wanted to show you how you might possibly have the slightest chance of coming up with one. And making things out of circles seems like a good strategy. Okay. And that little thing of like R being the percentage we're up to is really clever. Very nice. If you're very clever, you can choose your parameterization in such a way that none of the variables actually depend on the other variables. Okay. And then we're going to have to switch over to our new variables because it was originally in dx, dy, dz, so we're going to have to turn that into a dr, dv, d theta. And so we did a Jacobian, and then finally we were able to do that, except we also had to transfer our original function in terms of our new variables as well, and then we could do the integral one piece at a time. So one of the nice things about this integral is I could have, if I was being very focused, is to go, well, see this r and this v. No, this integral is in terms of r. No, yeah, sorry. This integral is in terms of r, and so this sine theta and this v cubed don't involve r, so they could come out of the integral. And then the integral involving r itself can come out of the full integral itself. And so because everything is sort of independent of each other in there, it's all multiplied together in separate pieces, I can actually do 3 separate integrals and just multiply them all together, and that would have given me the answer as well. I don't know if that's a thing in multivariable calculus that you've talked about, the ability to do that. So because everything's multiplied and I don't have v's inside r's and that sort of thing, I can actually just do the integral of the 3r squared and the integral of the v cubed and the integral of the sine theta and multiply them all together. Which is kind of cool because that means that with the sine theta I could have known it was 0 right from the beginning. Okay.
If you just done like the sine integral first,
then I would have gotten 0 as well, yes. So that's another point. If I had moved the thetas onto the inside and done the sine first, it would have come out to 0 way back then. And I would have had the integral, I would have got 0 and then the integral of 0 which is still 0 and then the integral of 0 which is still 0. That would have been nice. That would have been very clever. Not so clever today, but we're, another day. Okay. So let's try let's try the other side. So in this exam question that this goes with, there was an instruction that you didn't actually have to do the other side. You could say, oh, it's a divergence theorem, and look, I've already been asked to do the Jacobian and all this stuff, which is what I would do to do a volume integral, so I'll just do that. And then since I could use the divergence theorem, I'll just say the answer is 0, or whatever the answer is. But we're going to do both, just so that we have another practice at doing a surface integral. So now let's do the other end. Okay. So same deal. We're going to have to figure out what each of the pieces in this mean. We need to know what the boundary is, we need to know what the function is, we need to know what ds is. So I know what my function is, we were told that right at the beginning. Well, I changed it after that, but that's my f. Nice. I'm going to need to know what this is. Okay, so that W is a volume, which we drew earlier. This volume here. And its boundary is made up of 3 pieces. Because see this sharp edge here? that means there's a different piece. I'm not going to be able to just have one formula to represent the entire volume, entire surface. It's made of 3 separate bits. It's going to take me a while. I've got enough time, but we'll see how we go. I promised I would be home on time because my parents are coming for tea tonight. All right. Well. I did set the recording timer till 20 past. So.
Okay.
Okay. So it's the outside of this. It's the edge, the boundary. So it's 3 pieces. Which I am going to call top, the side, and the bottom. Okay? I should give them names. ST, SS, and SB. Okay, so the top is a circle. Yeah, a circle is just a line. Top is the inside of a circle, and the official name of that is a disk. So ST, disk. Yeah. Okay, and it's a disk of radius 2 at height 2. Okay, so the edge of this is x squared plus y squared equals... Actually, just a second. I'm not going to do that. I'm just going to run straight with it. We know what that is. We've already done this for the whole thing, right? We've made this disk. We've already made this disk out of all these little circles on the inside, right? And so it's going to be, and how did it go? The radius here is 2. And the height is 2, isn't it? Okay, so I've gone back to my other parameterization, which was here, and I've said, well, this is just this thing, but when v is equal to 2. And so I've just rewritten that. Beautiful. So I'm going to have to, or I'll just do all of them now, and then we'll deal with that in a second.
So the trick here is so you look at your earlier parameterization and you go, well, you just pick the values that are on the surface.
Yep. So let's do this one explicitly that way. It's my old parameterization. That is so not readable. At the edge, i.e. when r is equal to 1. And so it's v cos theta, v sine theta, v. I did have a theta before, didn't I? So v is in 1, 2, and theta is in 0, 2 pi. And then my bottom, the old at the bottom, i.e. when v is equal to 1. Beautiful. Okay, so it's 3 different pieces. And because my surface is made of 3 different pieces, I'm going to have to do each integral separately. which I really am pretty sure I don't have time to do, but we'll give it a go. Okay. Okay, so we're going to do...
This is something where you've got to check the orientation of the two circles.
Oh, yes, you're right.
Do you
Oh.
want to move the trick?
Just a second. Okay, so normally your normal, you want your normal to point outwards, I'd say. And so I need to go around that circle at the top that way, which is the correct direction. And I need to go around, whoa, okay.
Pointing outwards.
Yeah? I think that's how you do it, isn't it? So if this points outwards, on this edge of the curved surface here, if that points outwards, which is downish, I imagine that I could be going up the surface and anti-clockwise around there, and the cross product of those two would be out, as long as I did the correct one first. Okay. So I'm just thinking, damn, I've never done this before, so I'm so I need to pick two vectors so that the cross product of them is in the correct direction, and those two vectors are going to be my, my sigma sub v and my sigma sub theta. I just need to know which one to do first. And so sigma sub v, so that would be the correct normal, points outwards, and that direction is the one that follows around the circle, which is what the theta is doing. So I reckon I'm going to need to do, to get that in the correct direction. Yeah. And up here, my theta is going around that way, and my r is pointing that way, so I need to do, sorry, that's a v. I should do it in that direction, because my theta is going round that way, which is that arrow, and this arrow is the r going from the inward to the outward, and that's going that way, and so I need to go to r. Yeah, I think that works.
So the top is r cross theta,
Yeah,
and the bottom is
theta cross r.
I'm just in my brain, I'm getting it because in the question you gave earlier, we meant around.
Yeah, but we're not.
We changed the normal going the other way now, and we're still going the same direction.
Well, no, this normal was the same direction as the old one, because
Yeah, but to the surface it is different. Because the surface before pointing out.
yeah. So this one's backwards from the one, but the top surface of this is fine.
You switched across.
Yeah, a whole separate thing going on here. And so with this one, the r is still going outwards, and the theta is still going that way, but we need it to be pointing downwards, because that's outwards from the surface. This is on the bottom of the surface, so we need the normal to be going down when I'm on this bit. And so I need to go that way. So I need to have, that's the sigma theta and that's the sigma r. So I need to do theta cross. That's what I'm going to have to do for that one, to get the correct direction.
Which way is the one going?
Down.
In terms of direction. So,
Well, 0 to 2 pi goes anti-clockwise,
yeah.
and so changing theta makes you go that way. And r is from the centre outwards, it's a percentage, from here to there. And so the theta r is pointing that way, and the theta sigma is pointing that way. And so I need to cross them to get a vector that points down, which means I need to do that one first. Yes. If that doesn't make any sense to you, feel free to come and talk to me some other day. I'll be at Roseworthy campus tomorrow, so it will have to be another day than that. But I've only just figured that out, and so it might be wrong, but I'm pretty sure it's right. Okay. Thank you. Yeah. Yes. So this one down here should be the opposite of that one up there. So, okay. So I'm going to have to do each separately and do each integral separately. So, surface number top of, it's just f dot ds, isn't it? So the f was x, y squared 0, and the ds will be sigma r cross sigma theta times dr d theta. Right. I'll just figure out what all those things are, hey? Okay, so x, y, damn it, x, y squared 0, f is two r cos theta times another 2r sine theta, yep, and then 4r squared sine theta squared 0. Wow, sure.
So the original question, the right vector field was the disks at the top of the bottom turned out to be 0.
Yeah, that's all right. I'm not to be discouraged, because I can integrate sine squared, because it's a half of 1 minus cos 2 theta. No, but I don't have to worry about that yet, because I still have to times it by something later, and we'll see what happens when we get there. Okay, so I'm just going to pull that 4r squared out, because that looks like a good idea. Okay, and my sigma r is 2 cos theta 2 sine theta 0, and my sigma theta is minus 2r sine theta 2r cos theta 0. Cross product's going to be nice because of those zeros there. So that cross product is 0, that one is 0, and that one is 4r cos theta squared. Yes! 0, 0, but just for completeness' sake we've got that. And so my integral is now this. 4r squared. Oh, let's do the dot product now. Oh. So the dot product of my f dot sigma r cross sigma theta is now 4r squared cos theta sine theta squared 0 dot with 0, 0, 4r, and all the 0 positions means this is 0. Yay! And so therefore the integral of st of f dot ds is now the integral over st of 0 dr d theta, which is 0. Hi, how are we doing? Oh, we're doing well. So, let's do the bottom one, because it shouldn't be too dissimilar to this. Okay. Now, what did we say? It had to be round the other way. It probably doesn't matter which order the theta and the r are in over here, but it does matter here. Okay, so my f is xy, y squared 0, which is, according to this new parameterization, r squared cos theta sine theta, r squared sine theta squared 0. Not that we need to know this because it looks like it's going to turn out exactly the same sort of thing, but just for completeness' sake. So we need our sigma theta this time has to go first, and so that would be minus r sine theta r cos theta 0, sigma r is, oh, but we don't need to know this. We don't need to know any of this, because we know that the normal's pointing straight down anyway. I told you that right at the beginning, and then I didn't notice now. We know we don't need to do any of this. The normal's pointing down. It's just the vector 0, 0, 1. Well, I mean, of the appropriate size, though.
We've got the cross product to last question anyway.
But that's a different one though. It's slightly different.
Yeah, but it would be,
Just be a negative order.
yeah, because the ds could be interpreted as n hat ds. Yeah. It'll come out to 0 anyway, but that's okay. We could have done that. We could have said, well, no matter what the ds is, the n hat's going to be 0, 0, 1. So when they do the dot product, it'll come out to 0. But let's just do it the long way, because we're nearly done now. Yeah, that's the hard one.
Couldn't you just use the other cross product and say it's a negative and then just...
Well, it's not, because it's a little slightly different size.
Yeah, but you can see that in the first parameter you've got 2's, which gets out to 4r squared, and the other one, you get the r squared, so it should be a quarter.
Yeah. Is that what we got last time, or did we just get R? R. Okay, and so the f dot is 0. Good. And so therefore the integral is the integral over SB of 0 d theta dr, which is 0. Okay, good. So my last bit would have to be 0 as well, because they all have to add up to 0. Know what I'm hoping for. Don't need that anymore. Okay. All right. Now, what did we say that one was? Theta sigma cross theta v. Okay. So my VF this time was still so let's see, can I fit them all on the screen? So the x is v cos theta, the y is v sine theta, so v squared cos theta sine theta, and so v squared sine theta squared 0. Beautiful. I'm just going to have to be referring to something that's not on the screen. Yeah, look at that. So we've got that's minus v sine theta. So very similar, right? 1 this time, not a 0. Yeah. Oh, did I do that with v? This is a 0 this time, because I was doing theta. The next one's not going to be 0. Cos theta, sine theta, 1. Okay. This one was with respect to theta, so that one is 0. So we've got v cos theta in that spot. We've got v sine theta in this spot. And in this spot we have minus v sine theta squared and minus v cos theta squared. And so we get v cos theta, v sine theta, minus v. Right. Okay, so now we're supposed to dot product these. Oh, the minus v disappears anyway. Oh well. So what have I got? I've got v cubed cos theta squared sine theta. And I've got v squared sine theta squared sine theta. I've done that for a reason. And 0. Because this has got a cos squared and this has got a sine squared, so when they add together it'll be the other bit. Oh good, that sine theta is going to cause us to have 0 when we integrate it. Oh, is it?
No, it is supposed to be a v cubed.
Yes, v squared and v. Beautiful. So yeah, v squared times v is v cubed. Yes. Thank you.
How did you get from between those last two lines?
So this bit here is the same in both of these. So it's cos squared of this thing and sine squared of this thing, which in total is the thing. Yay! I'm doing, yes, I'm going to finish it.
Sine of 0, cosine of 0, cosine of 2 pi.
So my dot product is v cubed sine theta, d theta dv. And I'm going from v equals 1 to v equals 2, and theta equals 0 to theta equals 2 pi. So when I integrate with the theta first, like I should have last time, well, I know that's just 0, right? Are we allowed to just use that? That we know the integral of sine from 0 to 2 pi is 0? We could draw a little diagram if we like. Damn, that's not going away. 0 dv, and we can draw a little diagram in just a second. Okay, which is 0. So therefore, the double integral over my boundary of w of f dot ds, which was the sum of these three, is 0 plus 0 plus 0, which is 0.
So for Gauss, you always include that as in the top.
Yep.
But then you don't include the same percent.
No, because the inside of the surface, so for those who are listening online, for Gauss you include the piece on the top, and for Stokes you don't. And the reason for that is that in Stokes you're only interested in the surface itself, and it has to have a gap in it in order to have an edge.
Okay.
Yeah.
Okay.
Yeah. In order for it to have an edge around which to do the line integral, there has to be a gap.
So Gauss is you integrate the volume on the left-hand side, but on the right-hand side you reduce the volume to an area.
Yes.
So that's why you do surface integrals.
Yeah.
But for Stokes, you're starting with an area
Yeah.
that you then reduce to a line, which
Yeah.
is why you just take the edge.
That's
of
right. Yes.
the side hole.
Does that mean if you really wanted to, you could get the volume, reduce it down to an area, and then reduce it down to a line?
Only if you could reinterpret this f as the curl of something else.
Yeah.
So remember that you can't use Stokes' theorem unless this thing is already the curl of another vector function. And so if it was such that this f was already the curl of something, meaning that it's incompressible, I think is what it's called, then you can use Stokes to go around some other thing. But the thing is that then it would be 0, because this surface doesn't have a boundary. And so the integral around its boundary will be 0, because it doesn't have one.
Is that where something like the divergence of the curl or something equal to 0 comes in?
Exactly. Something like that, I reckon.
Divergence of the curl of a function is 0.
Yeah. So yes.
Because the function
If this function was already a curl, then back in the other thing we would have been doing the integral of the divergence of the curl, and the divergence of the curl is 0, and we would have integrated to 0, and we wouldn't have had to do any work. Oh yay!
So you can reduce it, but it becomes pointless.
Well, you don't need to reduce it because the original one would have
Yeah.
been 0 to begin with.
Yeah.
But you could ramp something up,
Yeah.
but that's not a thing. Where is this? Oh, it's over there. This one's movable. And look at that, just in time. Thank you, everybody. Right. I will go and... So sometime tomorrow, because I have to do all of the uploading manually. So it won't appear in your course, because I'm not in your course. So sometime tomorrow, I will email you with where this is. You're welcome.
That made a lot more sense than what it did in the course.
Now, to be fair to your lecturer, you've already done the course, and I'm putting a little bit on the end. But thank you.
Describing it as standing on an edge. Thanks, David.
You're welcome. Oh, I stole someone's exam. That's not it. Neither of those. Where did it go? Ah. Where did it come from? I didn't see it.